Suppose we play a game with a die where we roll and sum our rolls. We can stop at any time, and the sum is our score. However, if our sum is ever a multiple of 10, our score becomes 0 and the game ends. What strategy will maximize our expected score? And what is the optimal expected score? When choosing whether to continue rolling, we consider the probability of hitting a multiple of 10. If the unit digit of our sum is 1, 2, or 3, then we are guaranteed not to hit a multiple of 10. This corresponds to the range of being greater than 10k but less than 10k plus 4. However, if the unit digit of our current sum is not 1, 2, or 3, we have a 1 in 6 probability of hitting a multiple of 10. Suppose we know the expected value of our sum after we roll, then we can easily decide whether to roll. And the rule is as follows. If the expected value is less than our current sum, then we would rather not roll. Else, we would want to roll to get a higher expected value. It is difficult to get an explicit equation for the expected value, but we can compute the upper bound of the expected value. Then, we derive a sufficient condition to stop when even our least possible current sum is higher than the upper bound. Suppose our current sum doesn't end in 1, 2, or 3. In other words, it is bounded by 10k plus 4 up to 10 times k plus 1. Then, the best possible score we can get, with risking one multiple of 10, is 10 times k plus 2 minus 1. This can be obtained by rolling once, risking the probability of hitting a multiple of 10, and then rolling once without risk. For example, let k be 1, and our current sum be 19. Then, we roll once and get a 4. Now our current sum becomes 23. Next, we can roll once again without the risk of hitting a multiple of 10. And let's say we get a 6. Now our current sum becomes 29. And this is the best possible score we can get. Hence, the expected score of the roll is bounded above by this quantity, and it can be simplified to 25 over 3k plus 95 over 6. Now, a sufficient condition to stop rolling is if the upper bound of our expected value is lower than the least possible current sum. That is, 25 over 3k plus 95 over 6 is less than 10k plus 4. Finally, we derive k greater than or equal to 8. This corresponds to the current sum being bounded by 84 and 89 inclusively. The last step is to calculate the expected values backwards. Let ex be the expected value at sum x. Then, we initialize e of 84 equals to 84 up to e of 89 equals to 89 using our stopping condition. We also know that e of 10k is equal to 0 for all positive integers k. Then, we define this function f of x as the expected value of our ending score if we reached a sum of x and decide to continue rolling. For x not a multiple of 10, we get e of x using the following. It is equal to f of x if f of x is greater than x. In other words, we continue rolling. Otherwise, we will stop rolling, and the expected value is just equal to x. Finally, we work backwards to get all the values. Using the algorithm, we can compute the following table. Notice that for e of 0 up to e of 23, f of x is always greater than x. But for 24 and 25, x is greater than f of x. So, we should stop rolling at x equals to 24 or x equals to 25. On the right-hand side, we see that for 34 up to 39, x is always greater than f of x, so we should stop at these values. Because we have 6 of these values in a row, there is no way to reach 40 or above. Therefore, another stopping condition is if our current sum is greater than or equal to 34. Using this approach, the stopping conditions are x equals to 24, x equals to 25, or x is greater than or equal to 34. The expected score is E of 0, which is 13.2. As a follow-up question, let us change the rules. If our current sum is ever a multiple of 5 instead of 10, our sum goes to 0. What is the optimal strategy in this case? Check out the answer below.